All right, so chemical bonding 1, the Lewis model. We're going to touch on the Lewis model. I actually really like this quote. So theories are nets cast to catch what we call the world. So we cast out the nets to try and catch the world, to rationalize, to explain, and to master it. So to better understand the way the world works. We endeavor to make the mesh ever finer and finer. So you cast out your net, and you collect all this information about the world, and you try to explain everything as best you can, and you're 100% bound to miss things, or bound to explain things incompletely. And so then you take all this new information, and you construct a new theory, a finer net, and you throw that out. And you're able to define more things and explain more things, but you're still going to miss stuff. So continuing to just refine this model, or your model of the world, to be able to better explain it. It's a great analogy. All right, so bonding theories. One of them that you're familiar with, Lewis structure theory, right? Valence bonding theory explains why some molecules are stable and some are not. Formal charges help there. They also predict the shapes of molecules, and then the shape determines a lot of the chemical and physical properties, and we're going to get way more into shapes. Everybody loves shapes, and everybody knows that everything fits into the square hole. If you've seen that, sorry, it was a TikTok. We'll talk about the shapes in the next chapter a lot more in depth. And another bonding theory, actually. So different bonding models are useful in understanding different aspects of bonding. So I think you even saw in the worksheet on Monday's lab that Lewis theory works pretty well for a lot of things, but there's some places where it gets a little bit messy, especially when it comes to resonance and trying to optimize like which set of formal charges is better than another set of formal charges if they all add up to the same overall charge. So there are other theories that do a better job of that. So Lewis model is the one that we've done, representing all the valence electrons as dots. So those are the Lewis electron dot structures. I just usually call them Lewis structures or dot structures. It's the simplest model. It's really fast, really easy to just use valence electrons, draw a skeletal structure, and then fill in the electrons so things get octets. Yeah, and it'll actually does predict the shape of most molecules and if a molecule is likely to be stable through those formal charges. So why do things even form chemical bonds? Lower the potential energy between the charged particles that compose atoms. If you think about it, we've talked about this, that everything is made up of atoms. So why do the atoms stick together? They're optimizing these charges. A lot of elements don't exist in nature as elements. I think a great example of that is iron. If you leave iron out for any amount of time, it oxidizes into rust. Because that configuration, those bonds are more energetically favorable. And if you take rust and aluminum powder, you can make thermite, which releases a lot of energy to make products that are even more energetically favorable. Anyway, so as atoms approach each other, we get a complex set of interactions. The electrons are repelling, the nuclei repel each other, but then the electrons in the nuclei are attracted to each other. And if all of those interactions add up to a net reduction in energy, then you can form a bond. So ionic bonds, probably the simplest bonds to explain. I know metals have low ionization energies. It's pretty easy to form them into cations. Especially right, think about all of the transition metals. Their valence electrons are 4s2. They can lose those, and they've got all these d electrons underneath, and some of them will lose several of those. Nonmetals have negative electron affinities, so it's energetically favorable for them to gain electrons. So the metals will transfer their electrons to nonmetals. This is why all of our ionic compounds are a metal and a nonmetal. Let's talk about covalent bonds. So when nonmetals interact, they share some electrons, but they don't generally share them, well, sometimes they share them evenly. They're always really fighting so that they can have the electrons to themselves. So the most stable arrangement then, because they both really want those electrons, is to share them, sometimes unequally. And again, you're lowering the potential energy by forming those covalent bonds compared to any bonds that they might have had or not had before. So it's this sort of tug of war over that electron in the middle that causes it to be stable and causes the nuclei to stick together. Because this nuclei hates that nuclei. They hate each other back. But the electrons are what they're fighting over in the middle. They come together over a common goal. So I found this meme. Right? Covalent bonds, they don't want to give up any electrons. They share them. When you form ionic bonds, though, it's a very favorable arrangement. Now, metallic bonding is something else altogether. So metallic bonding occurs between metal atoms, and as it says here, nonmetals are all about my electrons, whereas metals are our electrons. And it actually doesn't get mentioned until the end of this chapter, but there's this like electron sea theory for metal bonding. So you have all these metal nuclei stuck together in this sea of electrons. Also partially explains why metals are conductive. There's a lot of electrons that just move freely among all of the metals. You got delocalized electrons. All right, so Lewis symbols and lattice energies. So we draw Lewis symbols for potassium and chlorine. Potassium is going to have 1 electron. Chlorine is going to have 1, 2, 3, 4, 5, 6, 7. And so by potassium really donating its electron to chlorine, we get these favorable electron configurations. So now potassium's got its octet from the row below, and then chlorine has a full octet on top. So then to rewrite these ions, right, we would get Ka+, and then for anions we get Cl, then all of these electrons, brackets, and a minus. Oh, I did leave this one in here. And Lewis structures actually do a good job even with more complicated things. So with that last one, we have transferring 1 electron, potassium wants to give 1 up, chlorine wants to gain 1. Easy math, 1 to 1. For other things, it's a little bit more complicated, but it's still pretty easy to figure out if we look at the Lewis structures. So we got magnesium, got nitrogen. Magnesium has 2 valence electrons. Nitrogen, actually I'm gonna draw it this way, has 5. So it doesn't exactly work out if we only have 1 magnesium and 1 nitrogen, because now the nitrogen needs more electrons. So if I add another magnesium though, now we got 4 electrons, but that's good enough for 1 nitrogen, but now this magnesium needs to give up another 1. So maybe we add another nitrogen, and now it can give up 1 electron to that nitrogen. And then maybe you can see where this is going. If we add another magnesium, now that magnesium can complete, and each of them can give up electrons as they need to or gain electrons as they need to. And then the formula for this, Mg3 N2, magnesium nitride. I think, okay, it'll come up. All right, so yeah, that happens. That's favorable. That's great. But there's a little bit more to this. It's not just the transfer of electrons that makes this favorable. Right? It's not just that magnesium wants to give them up and nitrogen wants to gain them. If we look at, and this is why we need to talk about ionization energy and electron affinity, the ionization energy, I guess in sodium chloride, is a positive 496 kilojoules per mole. So it takes a lot of energy to ionize sodium. The electron affinity for chlorine is only negative 349 kilojoules per mole. So this is to truly be energetically favorable, we need to have a negative kilojoules per mole. And this is only, would be a positive 147. But the delta H of formation, if you remember these, that's the amount of energy that's either released or absorbed when a compound is made from elements in their standard states, when you're making 1 mole. This releases 411 kilojoules per mole. So there's some disconnect between just this electron being transferred and whatever's going on here. And of course, it's in the title, and the whole reason I'm talking about it, it's the lattice energy. So there's this extra affinity because we make something like sodium chloride, or even the magnesium 3 nitride, and you might remember this from Chem 20, these don't exist as individual molecules. Like, there's not a molecule of NaCl. It exists in a lattice. So there's a lattice of, this would be like sodium chloride, because if you look at it, we've got one, I don't know, we call the red one sodium. So we got one red for every one silver, one sodium for every one chloride, but there's a whole bunch of them. Because of this, right, it would not be very convenient to describe an entire crystal of sodium based on the whole number of sodium atoms or the whole number of chloride atoms, and it could change. We can take this lattice, we can break the crystals. If you've ever had really fancy salt, it comes in like a grinder. So instead, we talk about it in the terms of the smallest whole number ratio between the two. So just NaCl, or MgN2. And so the formation of this lattice is the lattice energy. And that's where all of the extra stability comes from when you form ionic compounds. And what makes it so energetically favorable. So in theory, we're taking all of these sodium and chloride ions and then collapsing them or condensing them into a solid and emitting a bunch of heat. That's the lattice energy. So how do you describe this? Mathematically, we can describe it using Hess's law and the Born-Haber cycle. So the Born-Haber cycle is this hypothetical set of reactions that you would do to create an ionic solid. And we're going to use Hess's law and then the delta H of formation, and then each of the steps. So there's a whole process that happens here. So this is for sodium chloride. So we would start out with really the way I think about this is we're putting together the building blocks of sodium chloride one step at a time. So we can look at a table and we can find the formation of gaseous sodium to solid sodium. So we got to take it from, I said that backwards, formation of gaseous from solid. So if we want to take sodium and turn it into a gas, that takes a certain amount of energy. That's recorded somewhere. Somebody did that experiment. So we have that delta H. Then we need to take the chlorine, which is Cl2, and separate that into individual chlorine atoms. That takes some amount of energy. And these are all positive energy changes, right? So the energy has to go in to make each of these things happen. So once we've got our sodium in a gas, we've got our single chlorine atom. Now we take away one of the electrons on sodium. That's the ionization energy. And that brings us up to sodium positive, chlorine negative. And then really the second to last step is to take an electron and give it to chlorine to make the chloride. And so that gets you all the way up here to step 4. So the way that you calculate then this lattice energy is you take the delta H of formation. So you could find this equation to make sodium chloride and the heat released, which I think was negative 411 kilojoules per mole. And we subtract out all of this other stuff. And the difference between the energy to turn everything into a single atom of gas in its ion state and the difference between that energy and the energy of the delta H formation is the lattice energy. So basically say that there's a gap between these two numbers. The gap in between those has to be the lattice energy. I thought there was a calculation here. There's a calculation in the book where they go through those steps. It really, what it boils down to is looking up each of those values for each of those steps, trying to get everything into a gaseous state using the rules for Hess's law. So the lattice that you're making also changes the amount of lattice energy that gets released. So if we look at lithium chloride, sodium chloride, potassium chloride, cesium chloride, the size of those ions and the distance between the nuclei affects how much energy is there. And this has to do with Coulombic force. So the Coulombic force is, or Coulomb's law is F equals, I think it's K over Q1, Q2 over R. So R is the distance between the nuclei. So if R gets larger, Coulombic force gets smaller. So that distance decreases the energy. So as the size of each nuclei gets larger and larger, they get farther apart, less lattice energy. The other thing that matters here is the difference in charge. So again, Coulomb's laws is force equals K, Q1, Q2 over R. So we talked about the R portion, but the difference in charge also matters. So if we have like sodium fluoride, where the charges are both 1, essentially, right? 1 positive, 1 minus, 1 negative. And we bump up to a 2 plus, 2 negative, that drastically increases the lattice energy because the amount that they're attracted is dependent on the difference in the charges. So double the energy, and actually you get more than double. That's 4 times, a little less than 4 times, 3.5 or something, times the energy, just from changing the charges. So the two relationships here are, was it E? Yeah, they put E, okay. So the energy is proportional to 1 over the radius, or the distance between the two, as we get larger radii, larger atoms. And it's also proportional to Q1 times Q2. So increasing the difference in charge increases the energy. Increasing the radius decreases the energy. Cool. Huh? We'll talk about packing structures in a different, I don't know if it's the next chapter. I think it might be the next chapter. It's like the way that things pack together, because this wouldn't work for like the magnesium nitride, where we've got 3 magnesiums and 2 nitrogens. They'll pack together in a different form and make a different lattice. So I'm sure that has some effect on the amount of energy, but depending on how closely they can pack. Oh yeah, so how do we arrange these in order of increasing magnitude of lattice energy? So we're going to put, I guess we'll do it like this. Low, high. And we've got so which of these is going to have the lowest lattice energy? Huh? Yeah, so yeah, there's kind of 2 things you have to look at, right? The sizes and then the charges. So based on charges, well, yeah, based on charges, what's going to be the highest? Yeah. Maybe we should have started there. That's probably the easiest place to start. So that's the highest one. And now we can look at these 2, which are the same charges, but different sizes. Remember, as the radii get larger, they get farther apart, less energy. So potassium iodide is the lowest, and then lithium bromide somewhere in between. Probably closer to potassium iodide than it is to calcium oxide. Cool. Yeah.
Atoms increase in size when down the gravity?
Yeah.
So a smaller radius would mean more. So lithium bromide have the highest if the radius is the smallest. Which one should it say?
Lithium fluoride.
Lithium bromide is
If you want the 2 smallest radii of,
like lithium bromide compared to potassium iodide. But potassium and iodide have
oh, yeah, so lithium bromide would have the smallest radius, or a smaller radius than potassium iodide. Because potassium and iodide are going to be larger than lithium and bromide.
Okay.
Yeah.
Cool.
Yes. Because they're getting farther apart.
Okay.
Sorry, this slide for some reason is like a little bit funny to me because it's a little bit weird. We haven't talked about any of these things yet. Does our ionic bonding model explain the properties of ionic compounds? Just looking at this slide, what do you guys think? There's not a lot of, what are the properties of ionic compounds?
They're strong electrolyte.
strong electrolytes when they're dissolved. They're metal and a nonmetal. Do you remember if they have a high melting point or low melting point? That was kind of why I thought this was weird, because it's like, when was the last time you talked about or thought about ionic solids? Been a while. So they have really high melting points. So if you think about like these bonds between the ions in this lattice, you think it's easy to break those bonds. So to get a high melting point, that means it's really hard to get these ions to be able to move around in a fluid. And because we've got these opposite charges, and they really are locked together like this, because if we look at one of these, try to hold this so you can see it, like one of these in the middle, it's got a positive charge above it, below it, and on each sort of the four sides. So it's gonna be really hard for that to move and go anywhere. So if we wanna melt this, all 6 of these sort of need to be overcome by thermal energy, i.e. kinetic energy. Plus they're just really strong bonds because they're opposite charges. So it's gonna take a lot, it does take a lot to melt it. That's these non-directional bonds. Any ion in the middle of the lattice is not specifically bonded to a single other chloride ion or single other sodium ion. They're just held all together by these opposite charges. Ionic solids are also non-conductive. And if we're looking at the structure of this too, again, these ions can't move. So to be able to conduct electricity, we need the electrons to be able to move. But all the electrons that would be quote unquote free are locked up in the chloride. And so the charges in this aren't able to move. Now, if you were to heat this up and melt it, then it would be conductive. So if you had molten sodium chloride, it could be conductive. And if you dissolve it in water, it's conductive because we've dissociated these ions. They're no longer stuck to each other. So yeah, the ionic bonding model does do a pretty good job, right? We can look at the structure, huh? Right, because there's no ions to move. It's the same reason that pure water doesn't conduct electricity, right? In pure water, there aren't any free ions. As soon as you add sodium chloride, now you've got ions, and those ions actually act to transfer the electricity across. Okay, single covalent bonds. So this is where we're going to talk briefly about Lewis structures. Lewis structures, again, show how molecular compounds as neighboring atoms in which you have sharing of electrons to get octets mostly, some duets, and then also like boron and aluminum, where they only need 6 in some cases. So if we want to draw a Lewis structure for water, all right, skeletal structure, and then we'll have 2 lone pairs. Or for chlorine, and we show all of these electrons as either bonds or as lone pairs. So not bonds, right? We can also have double bonds or triple bonds in order to get those octets. So for oxygen, if you were to just draw the Lewis structure, whoops, too many electrons, 2, 4, 6, 8, 10, 12. And so then a pair of these gets shared out of their total valence electrons, and we get a double bond. And then for nitrogen, end up with a triple bond, which is what we see in reality. They also can show for compounds if they're going to be stable or not. So if we do H2O, which I've already done, right? H2O, we got hydrogens with duets, oxygen with an octet, that's stable. If we do H3O, so this should have, right, 6 for oxygen, and then 3 for each of the, 1 for each of the hydrogens, so another 3. So this has 9 valence electrons, which means that there's an extra valence electron on oxygen, which is not stable. However, if we remove that, if they remove that electron somehow, and we can get H3O plus, that would be stable. And H2O2 should be 14, so 2, 4, 6, 8, 10, 12, 14. End up with octets, so that's also stable. And we could even do, right, formal charges, so 0, 0, 0, 0. Pretty happy. And if we were to do it actually for the oxygen, 6 minus 1, 2, 3, 4, 5, yeah. So you end up with a positive formal charge on oxygen. So how does this work in reality? So remember, ionic compounds, non-directional bonds, right? This chlorine or whatever in the middle of the lattice can be bound to everything around it, to all of the positive charges around it. However, in covalent bonding, we end up with highly directional bonds. Whoops, that was the wrong one. Highlighter. Highly directional bonds. So just keep doing H2O. In water, this bond is only between hydrogen and oxygen. This bond is only between that hydrogen and the oxygen. It's not being shared with anything else in the solution, even if there are lots of water molecules around. Each molecule is its own distinct unit, only sharing electrons within that unit, which is why they form discrete molecules. And we'll talk more about intermolecular forces, but weak forces between in between molecules, or intermolecular forces, is what causes something to have a low boiling point. Bond polarity. So the electrons, I should say, the nonmetals don't like to share their electrons, actually. They do it because they have to. And some atoms, some nuclei, are more greedy for electrons than other. We call that electronegativity. So if we have unequal sharing, then we end up with polar covalent bonds. And so because of this, like, Lewis structures don't really show that at all. We just have this single line between two atoms, and that looks like equal sharing. But those electrons are actually, again, more like waves, kind of like particles. And so they're, in terms of the amount of time that they spend in any given space, is more like a cloud or sphere where you can find them. And so if something's more electronegative, like fluorine compared to hydrogen, those electrons are more likely to be around the fluorine than they are to ever be around hydrogen. So electronegativity is the ability of an atom to attract electrons to itself in a chemical bond. Fluorine is the most electronegative element. And because it's so electronegative, we've defined the electronegativity scale based on fluorine. Fluorine is just set at 4. We say fluorine's 4, everything's less than that. How much less than that depends on the element. The noble gases are unreactive. They've already got their electrons, so they don't care. So they're not included in these electronegativity trends. But again, these trends occur on the periodic table, and I like to base them again on the corners. Fluorine's the most electronegative. Francium's the least electronegative. And so anything that moves you closer to fluorine, more electronegative. Anything that moves you closer to francium, less electronegative. Left and down, lower electronegativity. Up and right, more electronegative. Arrange these elements in order of decreasing electronegativity. So phosphorus, sodium, nitrogen, aluminum. Decreasing. So which one's going to be the highest electronegativity? Let me highlight these on here. So do it like this. Phosphorus, nitrogen. Yeah, so nitrogen, phosphorus, aluminum, sodium. So why is nitrogen more electronegative than phosphorus?
Because it's closer to fluorine, and then phosphorus is one level down, right?
Yeah.
It's one level lower.
Yeah, exactly. That's what I was looking for, is that since we go lower here, right, part of this electronegativity is these kind of the valence electrons and how much it's able to grab or hoard valence electrons. So since phosphorus has another shell, those electrons are farther away. So it's harder for it to grab onto electrons.
So it's like the ionization energy, right? Where everything goes more towards helium, or in that direction?
Yeah, the ionization energy, yeah.
So they become
It's the same, yeah. Same trend. A lot of the trends go back and forth, or it's like francium is the most, well actually francium is usually the least, fluorine's usually the most. Depends on what you're talking about. They're the two extremes. So bond polarity, we can assign numbers to these things. Obviously that chart before had numbers on it for each element, what its electronegativity is. We determine what type of bond occurs, or we can determine, I should say, what type of bond is being formed based on the difference in electronegativity. So if it's small enough difference, then you get a peanut, yeah. And the electrons are equally shared. So no one atom has more of the electron share than the other. If you're between this 0.4 and 2, then there's going to be unequal sharing. We call that a polar covalent bond. If you got greater than 2, then you get an electron transferred, and that's where you get ionic bonds. You can also just write off ionic bonds as being metals and nonmetals. It's the only place you really get that large enough electronegativity difference. And yeah, the divisions are arbitrary. So it's a rule of thumb more than anything. If you are trying to determine if some new element or some combination of things was going to have a certain type of bond character, you could look at electronegativities, look at the difference, and before doing any kind of experiment, say, oh, it's probably going to have this kind of bond. When you get that uneven sharing, you get something called a dipole moment, which is whenever there's a separation of positive and negative charge, and it doesn't have to be a complete dipole. It could be a partial dipole, or I guess a partial charge separation. It doesn't have to be a full charge separation like in an ionic compound. You can calculate that. So dipole moment this is mu, not the Pokemon. Not spelled the same. This is mu. Mu is MEW. And then your distance, R is your distance. Again, keep using R because it's radius. And then Q is the charge magnitude. So how big is the charge difference? Another way we could look at this is percent ionic character. So using a ratio of the bond's actual dipole moment to the dipole moment it would have if the electron was transferred completely. So how big would the charge difference be? So how close is it to being a complete charge transfer? And we can see that trends pretty nicely with electronegativity difference. It has a little bit of a curve to it. And then even things like lithium fluoride and potassium fluoride, which we would think are like, they are ionic compounds, even that is less than 100% ionic character. So the biggest thing is how close are they on the periodic table? So iodine and iodine, if they formed a bond, would it be pure covalent, polar covalent, or ionic? Yeah. How close is iodine to iodine on the periodic table? Yeah. I think it might even be the same person. Doppelgangers. Yeah, so right, these are on top of each other. So that's going to be pure covalent. It's kind of like asking if you could beat yourself in a fight. It'd be pretty even. So cesium and bromine, cesium all the way over here, So how close are those on the periodic table? We're not considering the wraparound. Yeah, opposite sides. No. This isn't circular, right? So they're really far apart on the periodic table. And actually, well, we'll go ahead and do it. We'll go ahead and do it. Let's find these. Where'd they go? Cesium's 0.7. Bromine is 2.8. Cesium is 0.7 minus bromine, which is 2.8. So that's going to be 2.1. The difference, I'll put the absolute value here because math. So the difference is 2.1, which would be ionic. All right? And they're, again, super far apart on the periodic table. How about phosphorus and oxygen?
Pretty close.
Pretty close. They're like right there. And again, yeah, you can use the other information that you have here, the fact that there's 3 answers and we have 3 questions and we've used 2 of the answers. Process of elimination. But again, like if things are pretty close on the periodic table, probably going to be a polar covalent at most or a pure covalent at the least. And here too, we're going like different rows. Polar covalent. So this is ionic. If I really wanted you to calculate that, I'll give you the whole thing. Okay. It froze.
I may have missed it, but when would you know if it's polar or non-polar? I don't remember too well.
Polar covalent versus
Non-polar covalent.
pure covalent or non-polar covalent?
Yeah. Because even last semester was in Chem 20, we had an issue. Or like
It's-
it was hard for me to.
Usually, yeah, when I write questions like this, unless I want you to do something like really tight like these two, phosphorus and oxygen, I would say, because even I would have a hard time saying without looking at not those two in terms of the numbers. But phosphorus is 2.1, oxygen's 3.5. So you go and you would,
2.5 minus 2.1 or the.
doesn't matter. It's the absolute value.
Oh, okay, yeah.
Yeah, so that's 1.4. So if it's anywhere between 0.4 and 2.0, that's
Polar.
polar, higher is ionic, lower is nonpolar, which is the same as pure covalent. So perfect, like even sharing. Here, let's even look at this and say, which one of these would be, it's like sulfur and selenium. That would be nonpolar. Arsenic and selenium would be nonpolar. Phosphorus and sulfur, nonpolar. Carbon, nitrogen, that's 0.5. That's a little bit higher than 0.4.
Yeah.
Not much.
But would that be considered polar?
Yeah. If I gave you a question, I said, is this bond nonpolar or polar? Or is it, what kind of polarity is this bond? I would give you numbers. I'd say calculate it, and if it's higher than 0.4, polar covalent.
Okay, because I remember last semester we did the dipole and what was the other one?
Yeah.
It was like 3 of them. It was like non-polar.
Those are intermolecular forces.
Molecular forces.
And most of the time that comes down to either there being lone pairs.
Yeah.
Wait, yeah, we haven't gotten to that in the book yet. Yeah, if there are lone pairs on the central atom, it's going to be polar. If there aren't any, if the central atom has 4 bonds or doesn't have any lone pairs, then you got to look at the individual bonds. Usually I try to make those pretty easy. And I guess what I'm trying to point out here is that those are rare. So like carbon and phosphorus, wouldn't consider that polar. But if it's chlorine, bromine, well, bromine actually and carbon is not really. It's, because that's 0.3.
If anything, like on exam, you would give us the numbers just because we can't really tell what's.
Yeah, and I would try to make it something a little more obvious. In terms of that, like in reality, yeah, it's a little bit more, actually, here, I'll say this. Because it is a future thing that we're going to talk about later. What I really want you to look for is if this was like carbon, and then it's hydrogen, and then bromine. What you're really looking at on a molecule like this, is there one group that's different? And is that one group more or less polar than the other group? So here it's hydrogen and bromine. And again, how close are those in the periodic table?
They're pretty far.
Yeah, not at all close. So because this is going to be on one side of the molecule compared to the other side of the molecule, which is all the hydrogens, it doesn't even matter that this bond is technically nonpolar covalent. Bromine's more polar than hydrogen. or more electronegative than hydrogen. So it'll have a dipole moment. But we'll talk about that more when we get to it, yeah. This would only apply for anything that's just two things bound together. So if we had, yeah, it would be just individual bonds between things. So if it was like carbon monoxide, that carbon-oxygen bond is going to be slightly polar. And I think I would have to give you, for that one, I'd have to give you something. All right, give you the numbers. If it was sodium iodide, again, you can use that proximity on the periodic table. If it's anything that's really close, yeah, you're going to need some numbers probably to figure it out, unless it's something in fluorine.
It's like pretty far, like how like sodium iodine are far, it would be polar, right?
Definitely. Actually, this would be so far. This would be ionic.
Ionic?
Yeah.
Oh, that's right. Because the ionic is like a metal and non-metal.
Yeah, metal and a non-metal for that one.
Yeah, I didn't take that into consideration.
To go fully ionic, yeah, it's going to be metal and non-metal. All right, Lewis structures of molecular compounds. We made excellent time today. So these are the kind of the rules that we've already talked about, or that you've already learned through doing the Lewis dot structure worksheet. And I told you the one that wasn't on there, which is the, oh, even these instructions don't say it. But distribute among the atoms, giving octets or duets for hydrogen to as many atoms as possible. And I would say starting with terminal atoms. So starting with those terminal atoms, just things generally work out better. There are fewer situations where you need to completely move a pair of electrons from one atom to another atom without forming some kind of multiple bond, double or triple bond. And then formal charge. All right, so formal charge is the difference between the number of valence electrons and the number of electrons that it, quote unquote, owns in the Lewis structure. So this is why bonds only count as one. So in Lewis structures, we're assuming that everything's a nonpolar covalent bond, pure covalent. So that each atom is getting half of that bond's worth of electrons, so one each. So your formal charge is going to be the number of valence electrons minus non-bonding electrons, and then half of the bonding electrons. Or I just count the number of lines, right? The number of lines that are attached to it. So I did put one in here. Oh, yeah. Some rules for formal charges aside from that. When you're doing your Lewis structure, you want to try to, the sum of all the formal charges in a neutral molecule has to be 0. The sum of all the formal charges in an ion has to be equal to the charge of the ion. Sometimes there's multiple ways to do that. And small or 0 formal charges on individual atoms are better than large ones. So minimize formal charges. And then when they can't be avoided, I don't think this one was in the lab, negative formal charge should reside on the most electronegative atom. So if you can move things around so that your more electronegative atom, and this is just more electronegative. So again, closer to fluorine means that's the more electronegative atom. Try to put that negative formal charge on that. So put this one organic compound in here. What is it? Nitromethane. I think this is what they use in some racing cars. Drag racing? Huh? Yeah. Yeah. Yeah, the nitromethane burns your eyes.
When they put the engine, it burns off the exhaust, it burns your eyes.
Yeah. I've heard. I've never experienced. Don't really want to. So nitromethane, and this is a condensed formula, which indicates what the structure is going to be or the connectivity of the atoms. There's some assumptions that you have to make here. One of them being that hydrogen's not going to be anything other than a terminal bond. Hydrogen can't be in the middle. So we start with carbon. These hydrogens are going to be attached to that carbon. And then the nitrogen's going to be attached to the carbon. And then these oxygens will be attached to the nitrogen. If the oxygens were attached to each other, this would be CH3NO. Chanu. And then we've got, so 1, 2, 3, 8, 12, 24 electrons, 24 valence electrons. And we've got 2, 4, 6, 8, 10, 12 tied up in bonds. So it gives us 12 remaining electrons. And then again, starting with terminal atoms, hydrogens don't need any more. So we start with the oxygens, 2, 4, 6, 8, 10, 12. And then nitrogen needs more electrons. So we'll take a pair from an oxygen and put them in here. But we could have taken a pair from either oxygen, and those are resonance structures. And in reality, like neither of these electrons will have a full double bond. In reality, they'll have something between a single and a double bond. And this is one of the shortcomings of Lewis structures, that they don't really account for the true bond character that occurs in the actual molecules. For that, we'll use Vesper theory and hybridized orbitals. So this would be one Lewis structure, or other Lewis structure, or other resonance structure. Would be this. Oh, yep, sorry, that's a carbon. And then we can assign formal charges also. All right, for the hydrogens, they only have one valence electron. They only have one bond, so those are going to be 0. Carbon has 4 valence electrons, and it has 4 lines, so that's 0. Nitrogen has 5 valence electrons, but it only has 4 lines, so that's going to be a 1+. This oxygen has 6 valence electrons, 2 bonds, 2 lone pairs, so 1, 2, 3, 4, 5, 6. That'll be 0. And then our other oxygen only has 1 bond, so it'll be 6 minus 1 plus the other 6, so minus 7. So it's going to be negative charge. And then if we were to do these on this other one, all of these would stay the same, except for the oxygens would switch. And what's the most electronegative element in this molecule? Oxygen. So we've got our negative charge on the oxygen. And then this would be, neutral, because 1 negative, 1 positive. It's a neutral molecule, so that lines up. So there we got formal charges, resonance, and Lewis structures, all in one example. Free radicals are what happen when you have odd numbers of electrons. There's a whole branch of chemistry dedicated to these radical reactions. Radical reactions are used for most of the polymers, organic polymers that get made, because they're self-sustaining reactions. In Lewis structures, this means it's not possible for all atoms to have an octet. They tend to be unstable and reactive. So Lewis structures are useful for identifying these because they're not very stable molecules. So like nitrogen monoxide is only going to have 11, so 2, 4, 6, 8, 10, 11. There's 1 radical electron. Makes it tricky to draw. So we probably do something like that. And then oxygen, no, is a positive. And nitrogen, 1, 2, 3, 4, 5, 6. Negative. So maybe a single bond is better. Not a good molecule to draw, not a fun molecule to draw. So it doesn't exist. It'll exist, I guess, if you had a theory that this was part of pollution, it wouldn't be a great theory, and it probably exists as some other form. So Lewis model can't handle everything. You just do the best that you can, and you place the odd electron to minimize your formal charges. Anyways, we're not going to spend the time to do that. So which molecule would you expect to have a free radical?
Chlorine monoxide.
Yeah, whatever that thing is.
Chlorine monoxide.
So without having to count them, you can also just look at there's some atoms that just have odd numbers of valence electrons. Most common would be nitrogen, phosphorus, arsenic, or any halogen, right? Fluorine, chlorine, bromine, iodine, all 7. These are all 5. So you either need to have, this goes back to just like general math rule, right? How do you, odd numbers, you can multiply odd numbers to get even numbers, but you can't multiply even numbers to get odd numbers. So you have to have something with an odd number of electrons to get an odd number of valence electrons. So they're all going to have either nitrogen, phosphorus, arsenic, or another halogen. If there's just one of them, and there's not a charge on that molecule, then it's going to have, or I guess, and then not an odd number of hydrogens, then it's going to have a remaining electron, free radical electron. So like NH3 is fine. All right, end up with a good number of electrons, an even number of electrons there because we have 3 hydrogens. So 2 odd numbers added together makes an even number. But if we have NH4, this, without a charge, would have 1 electron left over. That's why NH4 has, or ammonium, has a positive charge to account for that extra electron. Aside from those weird free radicals, you can have incomplete octets. Interestingly, so BH3 will definitely do this thing where boron only has 6. For BF3, you have enough electrons floating around from fluorine that one of these can form a double bond, and boron can have an octet. But BH3, there are no extra electrons, so you can't form any double bonds. And then, so incomplete octets, and then the expanded octets. It helps if you use, instead of just going like the compass points, you can do the top and the bottom, and then a cross shape like this are the coordinates that'll get filled, and then this last one will be a lone pair. We'll talk more about those in the next chapter and the actual shapes that they make. Okay. We'll kill off this last section next week. But that shouldn't take very long at all.